Hi everyone. Today's lesson is going to be on some content that is actually not on exam 2. So this is content for exam 3. Oh, 1 second. For exam 3, not exam 2. So if you haven't had the second exam yet, feel free to spend some more time reviewing that before you watch this video. Just make sure you do watch this video between exam 2 and the following class, just so that you are ready for the following class, which is going to be like lesson 2 for the next exam. So again, this is not going to be covered on exam 2. This is for exam 3. Now, the topic of this lesson is one of the most ancient kinds of math. It's a little bit intimidating to some people if they haven't been presented it in a way that makes sense, but it's trigonometry. It's the study of angles. This form of mathematics originated with astronomy, as surprising that might sound. When looking at the night sky, it's important to understand the angles between stars is one of the best ways we can measure them, because we don't actually know how far away they are. And so talking about distances between stars from our perspective doesn't make a lot of sense, right? Like if you're a little person sitting here on Earth and you're looking up at the night sky, you can't actually tell how far away each star is from another star, right? Because you'll see one star here and one star here, but maybe this star is, 1,000 light years away, and this one is 100 billion light years away. But it's hard to, and so the distance between them might be further than it looks. But what you can measure is the angle between them. You can measure sort of how far apart they look from your perspective. We're going to get back to what this means what I mean by angle here in a second, for those of you who aren't familiar. But this study is sort of the origin of trigonometry. Astronomy was also used by sailors to help navigate in ships, and so a lot of actually the terms that we're going to be learning today, some of the terms we're going to be learning today, are actually old sailing words that mathematicians adopted to describe mathematical objects. We'll get to that again in a little bit. But the idea here is that trigonometry asks questions about how to measure, understand, compare, and solve problems involving different angles. In order to understand what I mean by that, we have to jump into talking about what the heck an angle is. So let's do that here. What is an angle? Zoom in here. Sorry, I'm still getting used to navigating. Okay. Still getting used to navigating here a little bit. So what is an angle? In order to talk about an angle, first we should talk about a ray. A ray is just a point in space. It's one point on a line, and all points extending in one direction from that point. Now this is a little bit of a formal definition, so we'll talk about what it means. But it looks like this. That's a ray. Here's another ray. Here's another ray. A ray is just a single point in space and a straight line that extends, sorry about that picture, a straight line that extends out from that point in only one direction, right? There's nothing happening this looks almost like a line, except lines go in both directions, right? Endpoints stop on one side. You can think about an endpoint is like partway between a line and a line segment. Like a line segment looks like this, and a line looks like this, but a ray looks like this. So I'll say line segment line, ray, right? That's the difference. A line goes on forever in both directions. A ray only goes on forever in one direction and has an end point in the other direction. Now, moving these off the screen here so we have a little more space. An angle is just what happens when you have two rays which share an endpoint. So, for example, if we have an endpoint here, one ray here and one ray here, that's an angle. Specifically, we like to think about this as the angle, but really the whole object is the angle. It's the endpoint and the two rays extending from it. Now, an angle, angles have, we like to just think of them as having an initial or starting side and a terminal side. In general, if you just see the two rays, it really could be either one that's the initial or terminal, like you could describe it however you want. But we like to talk about initial sides and terminal sides for this next definition. So, like, imagine you could say if this one is the initial side, then you would think about the angle as kind of going in that direction, starting at the initial side and going to this side, which we would call the terminal side. So, but you can just think of initial and terminal just means starting and ending sides. An angle in standard position, which is overwhelmingly the kind of angle that we will talk about in this class. An angle in standard position is an angle whose endpoint is at the origin, so point 0, 0 on the xy plane, and whose initial side points straight to the right. Or you could think about that, the mathematical way of saying that would be the positive x direction. So here I have a little picture of an angle in standard position, and you can see, and you can see its initial side, this lighter blue side, points straight to the right, and its endpoint is at the origin. The terminal side can point in whatever direction it wants, though its endpoint must also be at the origin because it has to be part of the same angle here. And we don't usually draw this curved arrow, but this kind of represents, you can imagine thinking about the terminal side starting out pointing to the right like the initial side, and you can imagine it rotating out this way. And the path along which it rotates, we call this whole space here is kind of thought of as the angle, if that makes sense. Basically, the amount of rotating it had to do to get from the initial side to the terminal side, we call the measure of the angle. And we measure that in a few different units. So, you can get back to the right file here. So I'll again give it a little example. So here is an angle where its initial side points to the right, and maybe here is its terminal side. So I'll say initial, terminal. Now, we use two different units to measure angles. And they're interchangeable. You can switch between them in the middle of a problem, though pay attention because some problems will ask you to give an answer with specific units. Just like we might use inches or feet or centimeters or meters to measure distances, and those distances might be the same measurement, but they might have a different measurement, like, 1 foot might be 12 inches, right? There are two different units that people use to measure angles. The first and more popular, or at least the one that you might have seen more often, is degrees. In degrees, one whole turn, like one turning all the way around so that you're pointing back the way you started, is 360 degrees. We use a little circle up there to represent degrees. Notice that it's not temperature, so you don't write Fahrenheit or Celsius after this. The angle is just degrees. And then there's radians. which are defined using the radius of the circle. Essentially, one radian is if you took a piece of string the length of the circle's radius. Radius is just the distance from the center of a circle to the edge. If you took a piece of string this length and you lay it across here so that this length is r2, and you measure this angle, the angle made between this initial side on the bottom and this terminal side up here that touches the other end of the string, that angle would be 1 radian. So like we would call this 1, this should say 1 radian, I just don't have enough space to write it. So again, it's like if you took a piece of string the length of the circle's radius and you laid it along the edge of the circle, the angle between the starting and end point of the string is 1 radian. The important thing to remember is that it takes 2 times pi radians in a whole circle. So that means that 360 degrees and 2 pi radians mean the same thing. They both say that's a whole circle's worth of angle. You turned around completely and ended up back where you started. The reason that pi shows up here is that actually pi comes from the definition of radian, sort of. It turns out that the number of radiuses it takes to get around the edge of a circle is exactly 6.282 blah, 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 blah. It's 2 times pi is the number of radius pieces it would take to get around here. So a little bit more than 6. Remember, 2 pi is a number, not another unit, right? It's about 6.28 because pi is about 3.14, right? So it takes approximately 6.28 radians to go all the way around a circle. These different measurements are, these different angles, these different units for measuring angles are useful in different situations, though they are, like I said, largely interchangeable. We can convert between them by remembering that pi, by literally actually just using this formula here, 360 degrees equals 2 pi radians. So if you have some number of degrees, if you want to convert them to radians, you multiply, I'll say, degrees to radians. You have to multiply your degrees by the number pi over 180. You could also think about this as 2 pi over 360, but that simplifies down to pi over 180. If you want to convert from radians to degrees, you do the reverse. You multiply by the reciprocal of that fraction. So you multiply by 180 over pi. And you can think about this as degrees here and this as radians up here. Radian. Does that make sense? So as an example, I believe we have a problem here. Yep. Let's take a look here. So this is a 30-degree angle, and we're going to be converting it. Oh, I did a little mistake on my layers here. One sec. Add a new layer underneath and fill that in with white. I should get rid of these little holes. There we go. Much nicer. Now, to convert, so again, to convert from degrees to radians, we're going to multiply by pi radians over 180 degrees. And so by multiplying by this fraction, you'll notice we started with degrees, then we're going to multiply by a number with degrees on the bottom, so the degrees are going to cancel. Here's what I mean. 30 degrees, you can think of this as 30 degrees over 1, right? Because everything is over 1, times pi radians over 180 degrees. Now, before thinking about what happens in terms of the answer, I want you to look at just the units. Here we've got degrees, and here we've got degrees. So if you think about units as a thing that can cancel out, those cancel, and the unit that we're left with is just going to be radians on top. So you can see how multiplying by this fraction of radians on top, degrees on bottom, is going to get rid of the degrees and just leave us with radians. This is a trick that also works in a lot of science classes, where if you want to convert from one unit to another, you always have to multiply by a fraction where the measure on the top and the measure on the bottom are in different they're in different units, but they equal the same thing. Pi radians is the same as 180 degrees. And you always want to multiply by the fraction such that the new unit is on the top and the old unit is on the bottom. That's just a general trick for converting units. But as you can see, the degrees cancel. 30 and 180 have a common factor of 30. 30 divided by 30 is 1. 180 divided by 30 is 6. So this is like 1 pi over 1 times pi radians over 1 times 6. So we get pi over 6 radians as our answer. And yes, RAD is the standard abbreviation for radians. If you prefer, you can write radians, the full word, RADIANS. But please do not leave it blank. It should either have a little degree thing after it, or it should say radians when you're talking about the measure of an angle. The same trick works for every problem here, so you can pause for a moment and solve these out, and then I'm going to do them really quickly. So here we've got 45 degrees over 1 times pi radians over 180 degrees. You don't always need to write the units while you're doing it, but I find the first few times it does help to keep track of it. Again, you can see your degrees cross off and your radians are left on top, so your answer will be in forms of radians. Again, 45 and 180 have a common factor. They have a common factor of 15 here. Actually, sorry, no, 45 goes into 180. They have a common factor of 45. 45 times 4 is 180, so this simplifies to pi over 4 radians. And also a good thing to keep in mind is these are some examples of some very basic conversions that you can just memorize, right? After you've done this conversion of 30 degrees to radians for long enough, you'll remember that it's pi over 6. Another way to think about it is that pi radians equals 180 degrees. So if you want to convert this back, you kind of can just plug in 180 for pi, and you get 180 over 6, or 30 degrees. Again, we'll get to that in the next problem, though. This last one down here, we do 60 over 1 times pi over 180. You can see, again, I'm not actually doing my my units here, but you can if you want to continue doing that. 60 and 180 are like, they simplify down to 1 over 3, and so this becomes pi over 3 radians. Notice that even though I didn't use units while I was working, I used them in my answer. Over here, we can do the same thing. 90 degrees, 90 over 1 times pi over 180 gives us 90 and 180 cancel to 1/2, so this is pi over 2 radians. Now, this is the standard of what you would see it written. You'll almost never see it written this other way, but if you give me your answer as 1/2 times pi radians, I will understand you. That said, and these are equivalent, right? Pi over 2 is equivalent to 1/2 times pi, just like x over 2 is equivalent to 1/2 times x, right? But be careful, because this is not the same as x over 2x, like 1x over 2x, right? Multiplying by x here is the same as multiplying by x just on the top, because it's like x over 1. So please never do something like this. This is not true. If you ever get like pi over 4 equals 1/4 pi equals 1 pi over 4 pi, the pi's cancel and you get 1/4. This is not true. Don't make that mistake, right? You can't 1/4 times something, you're not multiplying by the top and bottom. Multiplying on the top and bottom is a trick where you're actually multiplying by 1. So please don't make that mistake. You can go back and double check what that mistake was if you want to spend some time with that, but I'm going to move on. 240 times pi over 180. 240 and 180 have a common factor here of 60. This is like 4 times 60. This is like 3 times 60, so we get 4 pi over 3, or 4/3 pi. In either case, we would still write RAD or radians at the end. Notice 240 degrees is more than half a circle, and pi radians is half a circle, so this is more than pi radians. 4/3 pi is like 1 1/3 times pi. Now here, we just do the same thing. I know there's a negative, but that's fine. Negative 135 degrees over 1 times pi over 180. The common factor here is maybe a little uglier. I can't recall. They definitely have a common factor of 15, so I can start with... Oh, no, they don't have a common factor of 15. What do they have? A common factor of 45. So actually, this is quite nice. They have a common factor of 45. 45 times 3 is 135. 45 times 4 is 180. And so this is negative 3 pi over 4. Remember that negative was in front, so it's got to stay. And again, this is negative 3 pi over 4 radians. So that's our first problem. I can zoom out to show all the solutions here. So again, to convert from degrees to radians, you multiply by pi radians over 180 degrees, and that will always work. Now, going on to our next problem, we're going to do this in the reverse. So to convert from radians to degrees, we always multiply our radians by 180 degrees over pi radians. In a similar way to the last problem, this will always work out in terms of, this will always, like the angles, the units will always work out. So for example here, I start with pi over 3 radians. I multiply it by 180 degrees over 3 radians. Sorry, over pi radians. Please multiply by 180 over pi radians. That is in fact the trick. And you'll notice the radians cancel, right? You have radians on top, radians on bottom, so they cancel, and what we're left with is degrees. The pi's also cancel, right? And so we get 180 divided by 3, which simplifies down to 60 degrees, which makes sense because when we did this problem in reverse, we got the same answer, right? When we started with 60 degrees, our answer was pi over 3 radians. So when we start with pi over 3 radians, our answer should be 60 degrees. If you're better at converting in one direction than the other, you can always check your work by converting back. 3 pi over 4 radians, again, we saw this as an answer, well, we saw negative 3 pi over 4 radians, but if I multiply this by 180 degrees over pi radians, again, my radians cancel, so I'm left with degrees as my unit. 3 pi over 4 times 180. 180 and 4 have a common factor of 4, so that becomes 45 over 1. 3 times 45, we saw earlier, is 135. The pi's cancel, so we get 135 degrees. Now, if you don't do it that fast, that's okay. If you want to break it down, another way to think about this is this. When you do the multiplication out, right, you're going to get something like, let's see, 3 times 180, that's... What's that? 360 plus 180 is 520. 520 pi over 4 pi. And then you can just simplify this, right? Divide 520 by 4, which you could use a calculator to do, and the pi's are going to cancel, right? Or you could even go into a calculator and put 520 pi divided by 4 pi, and because the pi's cancel, it'll tell you it's exactly 135. Though you'll have to remember that your new angle is in degrees. So that's a different way to do it. If you don't like all that pre-canceling that I do when I multiply fractions, you can always just multiply them out and then simplify at the end. Again, here we're going to multiply by 180 degrees over pi radians. And that gives us here the pi's cancel, the radians cancel. 3 and 180 have a common factor of 3, so we can get that down to 1 and 60. So that gives us 5 times 60, or 300, over 1. And so this is still negative. Negative 300 over 1 degrees, which is just negative 300 degrees. Now, at this point, I do want to show you an alternate method to do this problem. Converting from degrees to radians, there's really one good way to think about it. But converting from radians to degrees, there is a little bit of a shortcut as long as there is a pi in your starting thing. A different way you could do this is you could instead think about plug in 180 degrees for pi radians. Now I want to emphasize that this is not an actual thing you do, right? Variables are a thing that we can plug in values to. What we're really doing is substituting 180 degrees for pi radians. So anytime you see a pi radians, you can replace that pi with a 180 degrees in parentheses. So like in this example, negative 5 pi over 3 radians. Replace that pi with a 180 degrees in parentheses. And we still got the negative here. And you get negative 5 times 180 over 3, and you can do the same multiplication out, which will still give you negative 300 degrees. So it is a thing that you can do. If there's already a pi in the expression for radians, if you replace all the pi's with 180 degrees in parentheses and simplify, you'll get the same answer as if you had multiplied by 180 degrees over pi. I'll let you think about why that is on your own. Now, the last one here, you can't do that trick for this last one. You have to multiply by 180 over pi because there is no pi in this, right? So 1 radian times 180 degrees over pi radians. Now the radians still cancel, but for once the pi isn't canceling, right? This is like 1 over 1 over here. So we get, by multiplying across, we get 180 degrees over pi. In other words, 180 over pi degrees. These mean the same thing, right? And what you could do here is go into a calculator and get an approximate answer. Like if you divide 180 by pi, remember pi is a number. So if I go to my calculator here and I divide 180 divided by pi, the real answer is 180 over pi. That's the best way to write it. But it is approximately equal to, notice I use this curvy equal sign for that, it's about 57.3 degrees. And here I just chose to round to the nearest tenth. Because I'm not doing a problem that says to round. Notice if you're not doing a problem that says to round, you probably shouldn't, right? Like the best answer for this problem is just 180 over pi degrees. But if you want to work with that number in a problem and you want to understand approximately how big it is, you can always actually divide by pi or kind of eyeball in your head dividing it by a little bit more than 3, right? 180 divided by 3 is 60. So dividing by pi, which is a little bit more than 3, will give you a little bit less than 60. Again, if the problem doesn't say to do this decimal approximation, I wouldn't do it unless you need to. And even if you do it, if the problem doesn't say to do it, don't make that your answer. Make this your answer. Because this is exact and this is an approximation. It's close to your angle, but it isn't actually equal to it. And so that's the whole problem there. Again, I'll zoom out. So like I said, any of these first 3 could be solved with this alternate method I put in purple, where you replace any pi's with 180 degrees in parentheses and then simplify. Like over here, 180 over 3 is 60. 3 times 180 over 4 does give you 135. So that trick works for all of the ones that have a pi in it. But obviously, if there's no pi in it, you still have to multiply by 180 over pi. So I'd get good at doing both things, and I would practice the version with the fraction first. Again, the way to remember which one of these fractions you multiply by is, think about, you always want the new unit over the old unit. If that makes sense, let me write this in a place where it actually fits. We always want the new unit divided by the old unit as the thing when we, that's what to multiply by. That's the version of this fraction pi over 180 or 180 over pi to multiply by, which is why you don't want to actually think about it as pi over 180 or 180 over pi. You want to think of it as pi radians over 180 degrees, or 180 degrees over pi radians. Keeping track of your units is very important in these kinds of conversions, or you will get very confused very fast. An important thing to note at this point also is that if you're ever going to, we're going to be talking about the trigonometric functions sine and cosine in a minute, and when you try and evaluate those in a calculator, which your calculator can do, you need to pay close attention as to the mode your calculator is in. Calculators have two modes, radian mode and degree mode. In radian mode, anything you plug into a trig function, they will assume is in radians. In degree mode, they will assume anything you plug into a trig function is a value in degrees. So be very careful when doing that in a calculator. Again, that's for the near future. Now here, we're talking about angles in standard position. We've already discussed what an angle in standard position is, right? In standard position just means its initial side, its end point is at the origin. Sorry, end point is at the origin, and the initial side points right along the x-axis. So here, for example, I'll draw my x and y axes for each of these problems. And then we'll probably do we'll do our angles in color on top of that to make it a little easier to see. So we'll do like a golden color here. All right. So here, by the way, this symbol here is just called theta. Oh, this gold is maybe a little bit too bright. This symbol here is just called theta. It's the Greek letter theta. T-H-E-T-A, theta. Sorry, I see that's off the screen. Theta. And just like how x is usually used to represent a number we don't know, the standard is that this Greek letter theta is used to represent an angle we don't know, the measure of an angle we don't know. So you can think of theta as like an x, but try not to swap between them in a given problem. Some problems will use x to represent an angle, and others will use theta. Theta is the more common one. But just be careful. In the middle of problems, it's not good to switch what your variables mean without a clear let statement describing how you're switching them. And even when you do that, you'll want to switch back by the time you answer the question. Now, here we have this angle theta equals pi over 4. Notice that they don't mention their whether it's degrees or radians. In this case, we can infer that this means radians from two things. One, they'll almost always say degrees if they mean degrees. They'll always have the degree symbol. And so if they leave it blank, it's probably radians. You are not allowed to do that. You are going to write RAD after every angle that's in radians so that you keep track. But sometimes mathematicians do leave it off, particularly if there is a pi in the expression and they actually do mean radians. So again, the other clue here is that there is a pi in the expression, and because we know a whole circle is 2 pi radians, any nice fraction of a circle will have to have a pi in its name. And so you can usually infer, if you see a pi, that your angle is in radians. But remember, our angle for part D of problem 2 was 180 over pi degrees, which had a pi in it but wasn't in radians. So it's not a hard and fast rule, so be very careful. But again, we can infer that these are all in radians in this particular problem. Now, we're going to draw this angle. Again, all of these angles are going to have the same initial side, right? The initial side of an angle in standard position must be starting at the origin pointing right. And then the terminal side, the other ray that makes the angle, is determined by the angle's measure. So this pi over 4, remember I said here that 2 pi is all the way around a circle? So pi over 4, you can think about, well, first of all, that means that 1 pi is halfway around the circle, right? So this would be an angle of pi, which means pi over 4 just means we break this angle up into 4 equal parts. Halfway would be here, and then breaking each of those into half, we'd get these like 45-degree angles, right? And in fact, if you convert this into into degrees, you get 45 degrees. And so some of us might know a 45-degree angle looks like this. Notice that I went clockwise from my initial position here, right? So we would call this angle pi over 4 radians, or we would call it 45 degrees. But the answer to the problem really would just be to do this, and then the nice extra touch you could do is draw this little arc between them without an arrow and label it with a theta. So this tells me the angle theta is the angle between these two rays in this direction. Because if you just have two rays, it's unclear whether like it's this one or this one, which is the whole reason that we did this defined standard position in the first place, is to remove that ambiguity. So that would be our answer for the first one. This is pi over 4 radians. It's a 45 degree angle. Here, pi over 2 radians, again, I said pi radians would be pointing all the way here, right? And so pi radians would be if the other ray pointed in the exact opposite direction, so it kind of looks like a line. Pi over 2 is half of pi, right? So that means that our terminal side is going to be up here. So this is a 90 degree angle, if you're familiar with those, right? Because again, 180 divided by 2 is 90. So again, we would draw the little arc and we would label that as theta. Notice that we're labeling these two things as theta because these are two different problems, and so theta can have two different values in those two different problems. Over here, 5 pi over 3 radians. The first thing to notice about 5 pi over 3 is that 5 over 3 is bigger than 1, right? That's not a proper fraction. And so this thing is bigger than half a circle because pi is half a circle. 5 pi over 3, we can think about, okay, we take the whole circle, or we take this, like, pi over 3 would be we take this first half a circle and we break it into 3 equal parts, right? This would be pi over 3. This would be 2 pi over 3. And so if I do that with the other half of the circle, this here would be this would be 3 pi over 3, right? Which is the same as just pi. That's why, again, pi is half the circle. This now would be pi plus pi over 3. So that's going to be 4 pi over 3. And this over here is 5 pi over 3. And so our actual answer to this problem, which I guess I'll do in another color since I did all this in gold. Our actual answer, which I'll put in a nice green, is point at the origin, initial side faces to the right, terminal side goes down here. And we don't label this as theta, because remember, we always start at the initial side and we go clockwise to get to the terminal side. This is theta. The outer angle, the bigger angle between the two. Again, you don't strictly have to do this labeling, but this is what theta is. It's this angle, not the little one. That's why we have standard positions, so that when we see these two rays here, we know that we're talking about this big angle, not the little one. Finally, we have negative 7 pi over 4, which is a little tricky. There's a few ways to think about this. Again, you could do the same strategy we did for the last problem and think about, well, what's 1 pi over 4? And then we'll just count by pi over 4s. Another way to think about this is a trick that we can, well, I'll do it that first way first, actually. So first, we're going to think about what's 1 pi over 4. Well, luckily, we actually already did pi over 4, right? It was this 45 degree angle here, because when you break pi up into 4 equal parts, you get those 45 degree angles. So negative 7 pi over 4 just means we start at the terminal side and we go counterclockwise, because it's negative, until we've done 7 of those 45 degree angles. So what I mean by that is this would be 1 pi, like minus pi over 4 would take us here, minus 2 pi over 4 would take us here, minus 3 pi over 4 would take us here, minus 4 pi over 4 would take us here, minus 5 pi over 4, minus 6 pi over 4, minus 7 pi over 4, which means our angle is right here. Now what I want you to notice, I'll do this in another color, go back to that green. So our final answer is this, and technically speaking, you could think about this as your negative 7 pi over 4. It's a little bit weird, but you can also actually, the way that things work out, because it's in standard position, we actually can still call this theta. This is negative 7 pi over 4. Now the fun thing about this is, because again, we started at our initial side and we go clockwise to our terminal side. The fun thing about this Although, like in this case, it's kind of valid either way to say that they're theta. Um, is look at this compared to our answer for A. It's the same exact angle. In fact, even though I just say they look like the same angle, I can tell you these are in fact the same exact angle. It is possible for like this one to be just like a little bit more and then they're not the same, but these actually are. Pi over 4 is the same angle as negative 7 pi over 4 because they end up in the same place in terminal position, in standard position. And so that gives us a new definition of angles being what's called coterminal. Coterminal, which again is just fancy language, angles have terminal sides in the exact same place in standard position. And as a note, sorry, let me zoom out my little recording setup here because I think it's doing more harm than good at this point. There we go. Coterminal angles have terminal sides in the exact same position. So an example would be the problem that we just did. The answer to A, this here, has the same exact terminal side as this here, even though their measures are written as different numbers, right? Pi over 4 is not the same number as negative 7 pi over 4. However, as far as angles are concerned, those numbers are actually equivalent to each other, essentially, in the sense of they create coterminal angles. So a rule about this: coterminal angles always differ by a multiple, and I'll say the measure of coterminal angles. The measure of coterminal angles always differ by a multiple of 2 pi radians or 360 degrees, depending on what units you're using, right? If they're both written in degrees, then you would be able to show that they are some multiple of 360 degrees apart from each other. If they're both written in radians, they're some multiple of 2 pi radians apart from each other. As an example, let's use that previous problem. It turns out that if you take negative 7 pi over 4 radians and you add 2 pi radians, right? 2 pi, we're adding fractions here. We're adding a fraction to a whole number here, so I'm going to rewrite this second thing as a fraction over 4 so that we can add them. They need a common denominator. Negative 7 pi over 4 plus, now this 2 pi as a number over 4 would be 8 pi over 4, right? Because that simplifies down to 2 pi. I just multiplied the top and bottom of that by 4, thinking of it as a fraction over 1. This is exactly equal to 1 pi over 4, which is exactly the other angle, right? This is the answer to angle A, to problem A here, and this was the answer to problem D. And so you can see if you add 2 pi to the answer to problem D, you get the answer to problem A, which is why we say they're coterminal. Because to get from one to the other, you travel the full circle, meaning you end up in the exact place you started with. It's possible that it might not be exactly 2 pi apart. It could be 4 pi apart or 6 pi apart or negative 8 pi apart. As long as it is a whole numbered multiple of 2 pi that separates them, then we call the angles coterminal. So this is true in both directions. If they're coterminal, then they must be different by a multiple of 2 pi or a multiple of 360 degrees. And if they're different by a multiple of 2 pi or a multiple of 360 degrees, they're coterminal, and we say in a sense that they are equivalent angles. But again, we like to use the word coterminal better than the word equivalent. I am just going to make a note. For many purposes, coterminal angles can be considered the same angle. This is not always true, and I'll point out when it's not true. But in general, as far as trigonometry is concerned, the angle negative 7 pi over 4 radians and the angle pi over 4 radians are basically the same thing. Note, by the way, if we convert this whole problem into degrees, we get negative, what is this? 360 minus, this is negative 335 degrees plus 360 degrees equals 45 degrees. Sorry, let's just say 45. Which means that negative 305 degrees and 45 degrees would be considered coterminal angles as well, because they're literally the same angles as this and this, right? They're just written in different units. All right, so in general, the rule is if they're different by a multiple of a whole circle, then they're coterminal, which means that they're effectively, they look and act like the same angle as each other. So again, that's like this and this. Those are coterminal. Now, often I will mention we like to, because coterminal angles are mostly considered the same thing, for many purposes, we prefer to rewrite angles that are not in the range of either like 0 is less than or equal to theta is less than or equal to 360 degrees, or 0 is less than or equal to theta is less than or equal to 2 pi. Like if they're not in either the interval 0 to 360 degrees, 0 degrees to 360 degrees, or 0 radians to 2 pi radians, we have a tendency to rewrite them as the coterminal angle that is in that range. A nice fact is that any angle you can write has some coterminal angle that is positive and less than a whole circle, or less than or equal to a whole circle, I should say. So for example, this, to get 430 degrees to be within the range 0 to 360, which is sort of the thought of as like the appropriate range for degrees to be written in, we do 430 minus a full circle, and we get here, let's see, 430 minus 360, that's going to give us, what, is that 70 degrees? I believe that's 70 degrees. And so what we would say is 430 degrees is coterminal to 70 degrees. That said, in this problem, they don't ask us to make a statement like that. They just ask us to give us that angle that's positive and coterminal and less than 360. So there you go. Oh yeah, I should actually say this range you can also think about as not including 360, because 360 degrees and 0 degrees are the same thing. Same thing with 2 pi. 2 pi radians is the same as 0 radians. They both represent pointing straight to the right, like an angle that has no measure. And so you can think of those endpoints as being parentheses on the right rather than brackets. They are brackets on the left, though. Right? So in the problem like this, you're always going to be trying to either get into the range of 0 degrees and 360 degrees, including 0 but not 360, or 0 radians to 2 pi radians, I should say radians, including 0 but not 2 pi. Again, same thing over here, but here we're below the range we're supposed to be, right? We want to find a positive angle less than 360. That's the same thing as saying that we're in this range. So we're going to add 360. Now, if this number was less than negative 360, we might have to add 720, which is 360 times 2. Or you can think about adding 360, and then if your number is still too low, add 360 again. Same thing with this. If you have a number that's super high, if you subtract 360 and you're still above 360, just keep subtracting 360 until you're not anymore. Eventually, by adding or subtracting increments of a whole circle, you will eventually get within the appropriate range. So this gives us negative 170 plus 360. What does that give us? Is that 190? Yeah, it looks like 190 degrees. Again, these are things you can do very easily on a calculator or in your head or on paper. And so we would say that, and again, I'm saying equals here. We wouldn't actually say 430 degrees equals 70 degrees. Sometimes we might say they're like congruent or something, but in this case, I'm saying 430 minus 360 equals 70, not that 430 equals 70. Same deal here. We're finding a positive angle less than 2 pi, so that's the same thing as saying that we're in this interval, right? That is coterminal with each of these. So here I'm going to add 2 pi, because that's a whole circle, and that gives me negative 5 pi. Well, then I need to add 2 pi again, and that's going to give me negative 3 pi. Still negative, so I add another 2 pi, which gives me negative 1 pi. Still negative, so I add another 2 pi, which gives me pi. So pi is my answer. Keep in mind the way this work is written now looks like nonsense because it looks like I'm saying this equals this equals this equals this, which is not true. But the idea here is just that I'm repeatedly adding 2 pi until I get a number that is actually in the range we want, right? So as long as it's still negative we have to keep adding 2 pi's until it's not. The other way you could think about this is think about, okay, well, what multiple of pi could I add that would get it into this range? And in this case, obviously, the answer is you could add 8 pi. Negative 7 plus 8 is 1 pi. 1 pi is between 0 and 2 pi, so that's our final answer. And again, we would write radians, even though this problem didn't write radians next to our number. Again, radians or rad is fine. Here we have 19 pi over 6. Now the thing with this fraction is it might be a little unclear whether or not this fraction is in this range or not already. So we have to think about what is the number 19 sixths? Well, 19 out of 6 is like, let's see, 18 sixths is 3. So this is like 3 and 1 sixth, right? Because this is like 3 times 6 plus 1. So this means that we're a little bit above our range because that means that this equals 3 and 1/6 times pi, which is more than 2 times pi. So if we subtract 2 pi, we're going to get like 1 and 1/6 times pi, which I suppose you could write this way, but this is pretty ugly. We don't like to have mixed numbers in the middle of an expression like this. So I would rewrite this mixed number as an improper fraction. This is 6/6 plus 1/6, so that's 7/6 pi, also known as 7 pi over 6. So we would write this as 7 pi over 6 radians. The other way to think about this problem is you can take this interval and rewrite its endpoints in terms as fractions over 6. So by multiplying them both by 6 on the top and bottom, you get 0 over 6 to 18 pi, sorry, not 18 pi, to 12 pi over 6, right? I just multiplied on top and bottom by 6 over 6. I multiplied by 6 over 6 there. So this is equivalent. They're the same numbers, right? And it's a lot easier to tell if 19 pi over 6 is in that range. It's clearly not. And then you can think about, well, 2 pi, as we just said, is 12 pi over 6, right? So instead of subtracting 2 pi, you can think, okay, 19 pi over 6 minus 12 pi over 6, because this is, again, this is 2 pi right here. That gives us 7 pi's over 6. So that's another way of thinking about a problem like this, is instead of converting your number into a mixed number or to understand whether it's a more or less than 2, you can just convert the endpoints of the interval, 0 and 2 pi, into fractions with the same denominator, and then it's a lot easier to solve the problem, right? Because 2 pi is the same as 12 pi over 6, so because we're more than that, we can subtract 12 pi over 6's until we get to a number that should be coterminal. Again, if you've got questions on this, please let me know. I know that these video lessons are not the ideal way to do this learning. Now we're going to move on a little bit to our next page. Sorry, I set this up multiple times. It was having some Photoshop issues, and so I needed to restart. Also, my dog was barking at the neighbors, and I did not want y'all to have sudden dog barking sounds in the middle of the lesson. Here we are. So a certain angle t corresponds to the point P on the unit circle. Find sine t and cosine t for the points P below. So this tells me I've got to give you some more definitions because most of this stuff is probably nonsense to you right now. So let's talk about now. We've talked about what an angle is. We've talked about how to convert between angles and things. Now we're going to talk about the real trigonometry stuff. time to talk about, well, let me change my color here. I only need to get my like palette swatches the thing set up. The unit circle. This is probably the most important object, the most important mathematical object that we will be dealing with in this unit, in our trigonometry unit. It's the most important mathematical object to trigonometry. The unit circle is just the circle centered at the origin, so its center is at the origin. Again, the origin is just the point 0, 0, where the x and y axes meet, with a radius of 1 unit, right? Feel free to follow along with me, take out a piece of paper. You can already graph the unit circle for me, right, with this information. It's a circle centered at the origin whose radius is 1. If I were to try and graph that myself, I would graph my axes, mark my little center here at the origin, and then I would think, okay, well, what are some easy points I can get on this circle? Well, some easy ones would be the ones that are on the axes themselves, right? A circle's radius is 1, so this length must be 1, meaning this point must have an x-coordinate of 1, and since it's on the x-axis, its y-coordinate is 0. This point over here must have the opposite. It must have an x-coordinate of 0, since it's on the y-axis, but because its radius is 1, and it's taken its radius pointing straight up, that means this is the point 0, 1. Similarly, this is the point negative 1, 0, and this is the point 0, negative 1. And we can just sort of do your best circle approximation in there. Let me see if I can get something a little bit nicer than that. The problem is I have to go fast on this tablet or it gets really wiggly. Sure, we'll go with that. So here is our unit circle, our lovely, lovely unit circle. This should really actually touch. Okay. And on this unit circle, we can talk about points along the edge of this unit circle, right? Like if I just pick a random point over here, hey, swatches, I wanted a different color. I can pick a random point over here. Sorry. Let's say I call this point P. And it turns out I can uniquely identify P, meaning I can say that P is basically the same thing as an angle. I can describe P just by saying that P is the point where the terminal side of an angle, some angle theta, touches the circle, right? So let's say, for example, that theta is, this looks like it's a perfect 45-degree angle, so let's say it is. So theta here would be 90 plus 45, which is 135 degrees, right? So that means that P, this point P, is the point made by intersecting this terminal side of my 135-degree angle with my unit circle. That should look more like it touches there. Yeah. Why do we care about this? Well, because it turns out that this is enough, sort of, to talk about the coordinates of P. Talking about the coordinates of P, right? There's some x and y value here that corresponds with this point P. And the question, a big question of trigonometry is, well, what are those? What's the relationship between this angle theta and the coordinates of the point P it makes on the unit circle? And it turns out that the definition of this is we have two new functions. Sorry, the x-coordinate of the point P we call the cosine of theta. This is not multiplication, this is function notation. So the cosine with theta, the variable plugged in. And the y value is called the sine of theta. Cosine is traditionally written C-O-S, and sine is traditionally written S-I-N, but it's not pronounced sin, it's pronounced sine, because the full words are C-O-S-I-N-E and S-I-N-E, but we abbreviate them for their function names. So we're using the unit circle here to define some really important functions. the sine, or I'll say the coordinates of a point on the unit circle. You can think of this as the point made by an angle theta in standard position. So we could think of this point P as the point made by this angle theta. R cosine theta, comma, sine theta. And again, where cosine of, we'll say x, and sine of x are functions. I'm just saying cosine of x and sine of x, using x as a general variable here. Sometimes you'll see cosine of x, sometimes you'll see cosine of theta. It depends on the way that they're writing in the problem. So here I'm just using cosine x and sine x to say that like they are functions of x, some variable you plug in. When I say cosine theta and sine theta in this definition, I'm saying that the actual angle in the problem, theta, is what we're plugging in to cosine and sine here. If that makes sense. But you could just as easily in your notes write this as cosine theta and sine theta are functions, right? And in fact, I might write it that way myself because I might want to extend this sentence to say where cosine theta and sine theta are functions of theta. What I mean there is just that the value of sine theta and the value of cosine theta depend uniquely on the value of theta. Once you know what theta is, you can plug it in, and just like any function, when you know what the input is, the output should be predictable. You plug it in twice, you should get the same answer. So this is all very nice that we just gave names to these new functions, and we just told you that their definition is that, keep in mind, this is the cosine is representing here the x value of the point P, and the sine is representing the y value of the point P. So you could just as easily make their definitions if the point is called xy. If we think about this point P as the point xy, like if its coordinates are x comma y, then x equals cosine theta and y equals sine theta. Sometimes people draw these without parentheses. It's a good idea, at least when you're getting started, to always include the parentheses to remind yourself that these are functions, right? Cos theta is not just a magical 4 letters that you write. Cosine of theta is the function cosine with the variable theta plugged in. Now, what the heck does any of this mean, right? Well, it turns out these functions, cosine and sine, are really important mathematically for all sorts of problems. If you study the way that the waves in the ocean work, or the way that sound waves work, literally any kind of wave, they are based on sine or cosine. If you study the movement of any rotational object, obviously, is related to sine and cosine. These are functions that are ubiquitous in mathematics. They're everywhere. And so, what the heck do these functions look like, right? Because we've been talking about these functions, we've been talking about functions in this class largely as these sort of visual objects, right? Like we can do calculations with them by plugging in x and getting y. We can maybe find their inverse by switching x and y and solving if we're clever. We can, but the main thing that we've been learning to do with functions is talk about them visually, right? What do they look like? What is the graph of them? How do we transform them? And so let's construct very briefly the graph of the cosine. I'll tell you a bit about the graph of the sine in a moment, but the sine and cosine functions are actually very similar looking, and so by talking about the cosine, we'll have done most of what we need to talk about the sine. So I'm going to draw a set of axes here. So we just got our x and our y axis, except they're not going to be an x and a y axis. I want you to think about this as our cosine theta axis. You could still, I guess, think about this as and our theta axis. What that means is the values I'm going to be plotting on the x-axis are values of theta, this angle, as it increases from 0 to the full circle. And the values I'm plotting, the vertical heights, are all going to be the value of the cosine function. Now, this is, by the way, the standard way to think about the cosine as input, because if you just replace theta with x, this is just x and cosine x, which makes a lot more sense, right? But this is sort of the standard way I want to think about it. Now, if it seems obvious to me, because of the way coterminal angles work, that the only important part of this function is what happens from 0 to 2 pi radians, right? Because that's going to be repeated everywhere else, which I'll explain a little bit more of in a moment. But here, I'm going to break this space from 0 to 2 pi up into 4 equal parts. Mathematically, you can just double check that that's what you get. You get pi over 2, pi, 3 pi over 2, and 2 pi. If you're confused by how I got these, I cut 2 pi in half to get pi, cut pi in half to get pi over 2. Halfway between pi and 2 pi is like pi plus pi over 2, which is 3 pi over 2. The other way to think about it is I cut it into 4 equal parts. 2 pi divided by 4 is pi over 2, and then this is like 2 pi over 2, which simplifies to 2 pi, 3 pi over 2, and then 2 pi is 4 pi over 2. This is just like a standard thing that people do, but this is what you'll usually see is pi over 2, pi, 3 pi over 2, 2 pi. Now, I'm going to ask you a question. I want you to follow along with me while we do this. Remember the cosine represents the x value of a point on the unit circle. I want you to stop thinking of this green point P as our point, and I want you to start imagining a point that starts over here, and we're going to have it move around in this clockwise direction, okay? So bear with me. We're starting right here at theta equals 0, right? The angle here would be theta equals 0. What is the x value of this point? That's right, I have it written right here. It's 1, right? The x value of this first point is 1, which means the value of the cosine starts when theta is 0, the value of the cosine starts at 1. So I'm going to plot a point at 0, 1 on my graph of the cosine function. Now, as our point moves up this way, right? As it moves this way, and it reaches this 90-degree angle, or this pi over 2 angle, right? This angle here would be pi over 2. We're going to get 0 for our x value, right? And so, but we didn't just go straight there, right? We didn't go like this. We curved on the way there. So our function is going to curve as well. So it makes this kind of curvy little motion downwards to pi over 2, to 0 when our input is pi over 2. Now continue moving your point in your brain along the circle and you get to here. Now our x value is what? Yeah, it's -1. So that means that we move down to -1 on our graph over here when our angle theta is pi, which is the angle associated with this. Now keep moving until we get 3/4 of the way around the circle. This is 3 pi over 2 radians. And that corresponds with an x value of 0 now. So we've curved back up to 0. Finally, curve back to where we started, which was at 1, and you get this sort of horseshoe shape, right? Now I said this is going to repeat in all directions, because if I go into the negatives, it's just like I'm going back along this way, right? These angles are equivalent, and so I'm going to have the same x value along the unit circle as I go. And so this function actually looks like this. Sorry, this is a very bad drawing. It looks like this, where it just keeps bumping up and down forever in all directions. We'll talk about this more in a future lesson, but I wanted to show you what I mean when I say sine and cosine right now. Sine and cosine are the x and y value on the unit circle, and they have this cool pattern that they do where they kind of fluctuate up and down. Now, when we're talking about the unit circle, the real thing we need to learn about it is it's useful to know some values that people have already calculated of the sine and cosine on the unit circle. So here, this is one that you might want to follow along with me and make a diagram of yourself. So we're going to draw that same unit circle, center at the origin with a radius of 1. That is a terrible circle. I'm in Photoshop. There's probably a circle drawing tool, but We're just going to call that okay. We have all this, right? And I already gave you the values of sine and cosine for some of these. Like, because again, this is like 0 radians. It's also 0 degrees, right? I think I'm going to write, I'll write it like this. 0 radians equals 0 degrees. And the coordinates of this point are 1, 0, meaning that the cosine of 0 equals 1, and this means that the sine of 0 equals 0. Does that make sense? Because remember, the point's coordinates are the cosine and sine of the angle that point, the angle created, the point created with an angle that has a terminal side in that direction, right? So if I go around the unit circle, we again have our other 3 points that we talked about. I said this here is pi over 2 radians, which is the same as 90 degrees. And this point here is 0, 1. So again, we have the fact of like sine of 1 is 1, sorry, sine of 90 is 1, right? Sine of 90 degrees is 1 because the sine is the y value here, or something like that. Now over here, we've got pi radians, and this corresponds with, which is the same thing as 180 degrees, and this point's coordinates are -1, 0. Over here, we've got 3 pi over 2 radians. This is 270 degrees, and the coordinates of this point are 0, -1. But the nice thing is, some early results in trigonometry actually give us a bunch more points on this circle. Specifically, we get every multiple of 45 degrees, so we get this point, this point, this point, and this point. So this would be pi over 4 radians, or 45 degrees. I think I'm going to start writing the degrees on the inside of the circle and the radians on the outside, and then I'll write the coordinates right after the radians. Here, this turns out to be the square root of 2 over 2 and the square root of 2 over 2. We'll talk about where these numbers come from in a little while. Here, we've got, this is pi over 4, this is like 2 pi over 4, so this is 3 pi over 4, which is the same as 90 plus 45, which is 135 degrees. And here, we've got, again, square root 2 over 2 and square root 2 over 2, but now we're on the left side of the y-axis, which means our x value is negative, right? Which makes it pretty easy to tell what's going to happen over here, because if we just vertically reflect this point, that's like switching the y value to be negative, right? So here, which is at 5 pi over 4, or what's this? 180 plus 45 is 225 degrees. This is these coordinates are negative root 2 over 2, negative root 2 over 2. You see, starting to see the pattern here? If you know a point on the top right, you can just change the signs of x and y to get the other 3 points, right? Because here is where x is negative and y is positive. Here is where x and y are both negative. And over here, x is positive and y is negative, right? So this one, which is, again, this is like 6 pi over 4, so this is 7 pi over 4 radians. And this is 270 plus 45 is 300 and, what's that, 35? No, 315. That can't be right. 270, no, that's right. I'm not crazy. I might have said something like 335 before, which may have been a lie. This is positive root 2 over 2, negative root 2 over 2, because again, on the bottom, what we call this the fourth quadrant. By the way, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4 as we go around clockwise like this, so sometimes called Q1, Q2, Q3, and Q4. We think about the order as starting on the top right and going clockwise. In the first quadrant, x and y are both positive. In the second quadrant here, x is negative, but y is positive, right? Because we're above the x-axis, but we're to the left of the y-axis. Over here, x and y are both negative, and over here, x is positive and y is negative, right? And that's just stuff that you should be able to figure out by looking. Any point in those quadrants has that property, right? Any point up here on the top right has positive x and y. Any point on the top left has positive y but negative x, things like that. So we've got those 4 points in now. I'm gonna, why do I do this where I draw all these extra things on top that I don't actually want? Let me, I want to get back to where I drew that circle, and oh no, drawing that circle and going around, I did everything after that, so we're gonna stick with it for now. So here, we also have one more point, and with this one more point, you can make the rest of the whole circle. This point comes from a very nice right triangle. This has, we'll talk about the right triangles inside the unit circle another time, but this point here is pi over 6, which is the same as 30 degrees. And so we're going to get every multiple of 30 degrees from this. So we're going to get points here, 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 and here. I'm not going to write them all out because I'm going to show you a picture of this in a second, but feel free to do so for yourself. Pi over 6 degrees. Actually, you know what? Fine, I am going to show you the right triangle for fun. You can draw a right triangle like this. Its hypotenuse has to be 1 because that's the radius of our circle. This has to be our x value and this has to be our y value, right? It turns out that this triangle has a height of, well, no, actually, I'm not going to show you. We'll talk about the right triangle another time. Pi over 6 has coordinates root 3 over 2 and 1/2. Again, this is the square root of 3 divided by 2, and this is positive 1/2. I know it's written a little weird. Which gives us a nice property over here. This is 2 pi over 6, or sorry, this is pi over 3, which is sometimes called 2 pi over 6. And it has the coordinates 1/2 root 3 over 2. They swap. And from here, again, by changing the signs of x and y, you can get these other points on the circle. That said, I'm going to pull up a nice unit circle diagram so you don't have to look at all my scribbles anymore. It's a little blurry. Sorry, just one moment here while I'm getting us a nice one. Here we go. So this is reminding you at the top that cosine and sine are the x and y coordinates respectively of each of these points. And so, for example, I can look at this and I can ask, well, what's the sine, the y value, of 5 pi over 6? And to do that, I go, okay, well, I find 5 pi over 6, that's over here. The sine is the y value, so the sine of 5 pi over 6 must be the square root of 2 over 2. So that's how we use this unit circle here. And some unit circle diagrams come with degrees. I can see if I can find us one that also has degrees here. I think it's nice to have both the degree and the radian measurements. Helps you compare. Yeah, here's a pretty classic one. Let's see if that's all picking up on the video all right. Yeah, so you can see this here. We've got, I'll sort of zoom in on my recording. Here they've got both the measures of each angle in both degrees and radians, and they've got the coordinates of each point. Notice there are the 4 points that are obvious, the 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Those are just obvious because they're just one unit in each direction from the center. That's got to be on our circle. And then these are the non-obvious ones. There's sort of 12 non-obvious ones. There's these 3 points, and then there's all of their reflections. What I want you to notice is that, like I said, if you know these 3 points, you know the whole diagram, because these 3 points on the top right, pi over 6, pi over 4, and pi over 3, they are just reflected. They just change their x or y values sign to get to any other quadrant. So if I want to reflect these over the y-axis, for example, right? If I want to, actually, I'm going to copy this image and bring it into Photoshop so I can doodle over it. Let's see if I can paste it in here. Come on, it's not letting me paste in. Actually, let me just then go like this. I promise I'm really good at computers, y'all. I studied computer science in undergrad and everything. Okay. So we've got our unit circle. What I want you to notice is that these 3 points are all you need. If you know the sine and cosine of 30 degrees, 45 degrees, and 60 degrees, you can get the rest of the triangle circle, because these 4 are obvious, right? These 4 just come from the points that you would, the 4 points that are definitely on a circle centered at the origin with a radius of 1, 1, 0, 0, 1, negative 1, 0, and 0, negative 1. But in order to, if you know these first 3, you can reflect them along the x and y axis. So if I look at this point here versus this point here, these are very clearly reflections of each other over the y-axis, right? They're the same distance from the y-axis and they're the same height. First of all, because they're the same height, that tells you automatically they have the same y value, right? But more importantly, being a reflection of somebody over the y-axis just means that you have the same coordinates, but your x values have opposite signs. So to go from here to here, you just make all the x values negative. That works for this point. The x value just turns negative and nothing else changes. And it works for this point. The x value just turns negative and nothing else changes. So, don't know what Photoshop was trying to do there. So the important thing to notice there is that that happens in all 4 quadrants, right? If I want to take this point down and get this one, notice I didn't take this and get this. I took it and got the one that's the same distance away from the axis I'm reflecting over. I just have to turn its y values negative because I'm going from the place where x values and y values are both positive to the place where x values are positive but y values are negative. And to get from here over to here, I just have to make the x value negative because I'm crossing over the y-axis, right? And so as long as you know these 3 points, you know the whole diagram. And the wild thing is, you don't actually even need to know all 3 of them. Because if you know these 2 points, you know the whole diagram. Because if you look here, this point, like I said earlier, is just the same as this one, but with its x and y values switched. So while yes, we are going to have you memorize the unit circle, memorizing the unit circle means memorizing these 2 points on the unit circle, because you can construct the unit circle if you just have those 2 in your head. And I will show you in other lessons other ways to get that memorization of the unit circle, to find out what these points are, because there's actually nice ways to find them. But those are a lesson for another time. For right now, I want to take us back to our problems, because I think I've diverted us long enough. A certain angle t corresponds to the point P on the unit circle. Find the sine of t and the cosine of t for the points P below. So remember our definition. P equals sine of theta, sorry, not sine of theta, cosine theta. Cosine comes first, cosine is the x value. Cosine theta, sine theta for the point P made by, oh, I see I'm still zoomed in here. Oh my goodness. Made by the angle theta, right? If that's the case, they're saying the angle isn't called theta, it's called t. So if I go back in here and I replace all my thetas with t's, I find out that, oh, the answer is just going to be pointing to one of these numbers, right? If they want the sine of it, I have to look at the y value. If they want the cosine, I look at the x value. So the cosine of, we would say here the cosine of t, because t is the angle, right? A cosine is a function that takes in an angle and gives you out an x value. The cosine of t is the square root of 3 over 2. It's this number here. And the sine of t is 1/2. And that's it. That's all you have to do for part A. They're just using the fact that the coordinates of a point on the unit circle are always the cosine and sine of the angle that made that point. Here, same deal. The cosine of t is the x value of our point, -1/2. Whereas the sine of t is the y value of our point, √3/2. We're done. We don't even have to know what the angle t is, though if you look at your unit circle, you can probably see pretty easily what angle t actually is in these problems. They're not actually asking you for it. They just want to know what the cosine and sine of t are. That's a trick that you'll see a lot in trigonometry, where you pay attention to what they're asking you, because sometimes you don't need to find certain things in the problem to find what they're asking you. Like, we never have to find what t is to be able to tell them what cosine and sine of t are. Again, now they're going to ask us to use our unit circle here. So you can take a pause and use a unit circle diagram to answer all these problems. They're just saying find the values of sine and t and cosine and t, the all is a little silly, when t equals this. So here, again, these are clearly in radians. We're asking the sine of pi/2. So if I want to find the sine of pi/2, I go back to my unit circle diagram. I look for pi/2, which is right here. It's the 90-degree angle. And I ask, what is its y value, right? Because x equals cosine theta and y equals sine theta. So we want to know our y value if we want to know the sine. So that's 1 here, meaning going back here, sine of pi/2 is 1. Cosine pi/2 is the x value of that same point on the unit circle made by this pi/2 angle, this 90-degree angle. The x value of this point is 0, so my answer is cosine of pi/2 is 0. And now we move on. That's it. That's all you do for that problem. T equals pi. So again, we go back to our point here, to pi radians, which is 180 degrees, and we see that the cosine is -1 and the sine is 0, so I can say cosine pi is -1, sine of pi is 0. So again, these are functions, and they're weird functions, but we can find some of their values by using our unit circle points. Again, t equals 3 pi/2. I go back to my unit circle, find my 3 pi/2 angle. That's down here. The point that that angle makes is right here, and that point's coordinates are 0, -1. Remember, this is the cosine of 3 pi/2 is 0, and this is the sine of 3 pi/2, because the cosine is the x value and the sine is the y value. So that means the cosine of 3 pi/2 is 0, and the sine of 3 pi/2 is -1. Notice, it doesn't matter what order you tell me what the cosine and sine are, but don't mix them up, right? You wouldn't say the cosine of 3 pi/2 is -1 and the sine of 3 pi/2 is 0. That would be incorrect. Now over here, pi/4, again, we can just reference our unit circle. Pi/4 is right here, so this is our cosine and this is our sine, because it always goes cosine and then sine. So in this case, they're both the same thing. So we would say the cosine of pi/4 is √2/2, and the sine of pi/4 is also √2/2. Now again, we're just going to do the same thing for these 2 points. T equals 3 pi/4. We find our 3 pi/4 here. Might take a second, but 3 pi/4 is right here. It's 135 degrees. Looks like our cosine is -√2/2 and our sine is +√2/2. So I would say that cosine 3 pi/4 is -√2/2, and sine of 3 pi/4 is +√2/2. Finally, 5 pi/4, that's down here, and they're both -√2/2. So we get cosine 5 pi/4 equals -√2/2. Sine of 5 pi/4 equals -√2/2. I will say I will allow you to drop the word radians if you're plugging an angle in to a sine or cosine function. Don't drop the degrees symbol if you're using degrees, but if you're using radians, you can drop the word radians when you're plugging it into a sine or cosine function, if that makes sense. Like I don't have to write sine of pi over 2 radians here. That just takes a lot of time and space. So if there's no degrees, if there's no degree symbol, I'll always assume radians if it's on the inside of what's called the argument of a trig function. An argument is just what's in the parentheses. All right, now here's a fun one. If cosine of t is 24/25 and t is in the fourth quadrant, find sine of t using a trigonometric identity. So this means I've got to teach you some trigonometric identities. Our trigonometric identities that we're going to learn for today are there's a very nice important one that comes from a beautiful thing you can do with your unit circle. I'm going to draw ourselves another circle. There's going to be a lot of circle drawing in this unit, just FYI. So we've got our unit circle again, right? So those are 1 0 0 1, etc. I'm not gonna. You don't always have to label it like this, but I'm going to do it today. Right? Let's say I have some point on my unit circle. A neat trick I can do is I can what's called inscribe a right triangle just like this. I connect my point to the origin, and then I drop a line straight down to the x-axis so that it makes a 90-degree angle. And that makes a nice little right triangle, right? Now, this right triangle is sort of a magic trick in the math world because it shows you how triangles and angles and circles are all related. This right triangle has this angle here being theta, right? The corresponding angle that made this point P here, if we want to call this P. But what are the lengths of these two sides? Well, I know that P's coordinates are cosine theta, sine theta, right? So this is its x coordinate, this is its y coordinate. But this line is the x coordinate of P, right? It's the distance that P is from the y-axis. It's the same distance because of that 90-degree angle, which means this side must have length cosine theta. And this side is the y coordinate of P, right? Because it's the height of the line P off of the x-axis, meaning this must have sine theta as its length. And this is 1 because that's the radius of our circle, meaning we have this beautiful right triangle whose sides are cosine theta, sine theta, and 1, and this is the angle theta, right? Now, there's a lot that you could notice here. If you know the SOHCAHTOA definitions of sine and cosine, you can see that they agree with this. In fact, this is sort of where they come from. But the more important thing to note here is Pythagoras, who turns out may or may not have existed, but there were definitely Pythagoreans in ancient Greece, and they definitely pretended a guy named Pythagoras existed if he did or if he didn't. But the Pythagoreans came up with a really lovely formula about right triangles and right triangles only that says if this is A and this is B and this is C, right, then we would say A squared plus B squared equals C squared. This is called the Pythagorean theorem. Ask me sometime how they would have looked at this phrase if you ever showed it to them, because they came up with this theorem long before algebra existed. But if we plug in the values we actually have for A, B, and C here, we get a lovely little formula, which is cosine squared theta. This just means the cosine of theta squared. It's just notation so that you don't think that it's theta being squared, it's just cosine being squared, plus sine squared theta equals 1 squared. But of course, 1 squared is just 1, so we can drop that squared out. And we get this, which is called the Pythagorean identity. This is the most important trigonometric identity I will teach you this semester. It is the most useful one. If you have the square of the cosine added to the square of the sine, you always get 1, as long as they're taken up like the same angle, the same theta. Now, looking back at the problem, let's see if we can use this identity to answer the question, right? So if cosine t is 24/25 and t is in the fourth quadrant, we'll talk about why they're telling us about the fourth quadrant in a second. Find sine of t using a trigonometric identity. Well, let's see. Cosine squared t plus sine squared t equals 1. Again, this squared notation is the same thing as if I wrote the squared like here, but that's a lot of parentheses, so people just tend to write it like this. If we plug in, we're going to get 24/25 squared plus sine squared t equals 1. And we can solve this, right? We can square 24/25, which is the same as just squaring 24 and squaring 25. So let's see, 24 squared is 576. 25 squared, I should know, but I don't off the top of my head, is 625. So 625, 576 plus 6 over 625 plus sine squared t equals 1. Now they say they want us to find sine of t, so we're not solving for t, we're solving for sine of t. We want to isolate sine of t. To isolate sine of t, we should subtract this 576 6/25 from both sides, so we get sine squared of t is equal to 1 minus this, which is like 625 minus 576 over 675. 625 minus 576, I'm again not going to do, is 49 out of 625. And now we just take the square root of both sides, and we get sine of t is plus or minus 7/25, because we can again take this the square root of the 49 over the square root of 625. Now here's where t is in the fourth quadrant comes in. There's two possible answers, but only one of them is right for t being in the fourth quadrant. T is in the fourth quadrant, right? So that means that x is positive and y is negative. I had that in our old unit circle diagram over, did I erase it? No, it's over here. X is positive and y is negative in the fourth quadrant. And remember, x is the cosine and y is the sine. Since we're looking at the sine, that's a y value, it should be negative in the fourth quadrant, meaning our answer is the sine of t equals negative 7/25. Again, we just used the Pythagorean identity, which is basically just the Pythagorean theorem, to find sine of t is plus or minus 7/25. And then in the fourth quadrant, the sine, being a y value, must be negative because we're below the x-axis. So our answer is negative 7/25. Now here they're saying use a reference angle to find the value of the following. A reference angle is the angle made with the x-axis for some other angle. So what I mean here is the sine of 315 here. 315 is more than 270, so it's here in the third quadrant, right? 315 degrees. Instead of thinking about 315, I want to think about this angle, the angle that I'm making with the x-axis, and that you can pretty easily see is going to be 360 degrees minus this 315, right? And so that is going to give us 360 minus 315 equals 45 degrees. Now, the thing about this is, it turns out that sine and cosine, if you look back at our unit circle, this is basically just saying, what's the original one of those 3 points on our unit circle that you actually correspond with, right? Because if we look over here at 315, right? It's got the same coordinates as 45 degrees does. It's just got different signs, right? And if you look at what the reference angle of 315 is, it's 45 degrees because that's the angle here that got reflected over the x-axis, right? So by looking at what its reference angle is, that's really telling us which of these 3 points it's getting its values from. And in this case, it's getting it from pi over 4. So we look and we see it must have root 2 over 2 and root 2 over 2 are its cosine and its sine. And so ours are going to be positive root 2 over 2 for cosine, but negative root 2 over 2 for sine, because again, we're in the fourth quadrant, and our y value has to be negative in the fourth quadrant. So here, we know that the sine of 315 degrees is going to be equal to the negative sine of 45 degrees, which is going to be negative root 2 over 2. Same deal over here, but we're working in radians. Here, negative 5 pi over 4. That's going to be a little trickier because we have to actually figure that out. They're not going to label negative 5 pi over 4 for you. So you could add 2 pi's to it until you get what you want, or you could actually like count backwards by pi over 4s. Pi over 4 is like an eighth of a circle like this. So 1, 2, 3, 4, 5 brings us here. Our reference angle is the angle that this makes with the x-axis. And so this is 180 degrees, and this is 135 degrees. So to find this difference, we're going to do 180 minus 135, which gives us, what's that, 45 degrees. So again, our reference angle is this, right? Which makes sense because we are a reflection of this point. So the idea of a reference angle is the same as the idea I was saying before about how each of these like 12 hard points to remember are just reflections of those first 3 points. The reference angle here is 45 degrees because this is the reflected version of the 45 degree angle. Again, that means that it's very easy to tell what its coordinates are. I know that the sine and cosine of 45 are root 2 over 2 and root 2 over 2. So the cosine of 45, and again, this angle is in the second quadrant. We said it was over here. So in the second quadrant, the cosine, which is the x value, should be negative. Note that that has nothing to do with this negative. It's because of the quadrant we're in. We're in the second quadrant. So cosine of negative 5 pi over 4 should be equal to the negative cosine of pi over 4. So it's, again, negative root 2 over 2. Again, this negative isn't coming from here and going to here. It's coming from we're in the second quadrant. So cos slash x is negative. Remember, cosine is an x value. X values are negative in the second quadrant because we're to the left of the y-axis. And finally, find the coordinates of the point of the unit circle at an angle of these. This is just easy. This is just your unit circle diagram, right? So pi over 6, root 3 over 2, 1/2. And 5 pi over 3. 5 pi over 3 is here. That's 1/2 negative root 3 over 2. All right, and that's the whole worksheet. I know this was a lot to take in, and we're going to be repeating a lot of these ideas, but please ask questions as soon as you have them. You can ask them publicly in class. You can send them to me in emails, though I think asking them publicly in class is great because I guarantee you there are other people asking the same, who want to ask the same question. Don't be one of those people. Don't be one of the people who waits for somebody else to ask your question. Please just ask your questions. Trigonometry is a lot at first, but all the ideas are really closely interrelated. So once you start understanding some of it, it will help you understand the rest, I promise. Please come to me for support, come to the tutoring center for support, talk to your classmates for support, look at the internet for support. Trigonometry is wild and cool, and there are a lot of definitions. Do not get overwhelmed. It's going to be okay, but you have to put in the work to make sure everything makes sense to you. All right. Have a great day, and I'll see you soon.